So let's put this into the Euler-Lagrange formula and find our differential equations of motion. So let's first do with theta 1. Right? So the Euler-Lagrange formula for theta 1 would be d theta 1, and I use this purple for theta 1 minus, maybe I'll go back to green, d dt of dl d theta 1 dot, and all of that equals 0. So let's put this in here and see what we get. So let's do the first term first. dl d theta 1. So we're looking for all of the terms that depend explicitly on theta 1. So this is theta 1, but it's theta 1 dot, so we'll ignore this term. Same with this term, same with this term. This term has a theta 1 dot in it, so we need to keep track of this. And these two terms also have theta 1 in them. So we'll have these three terms here will all be in this dl d theta 1. It's partial derivative. So the first one we'll do is this one. So we won't pay attention to these, and we'll just use this. So all the constants out front, right? Theta 1 dot is a constant when we're taking the partial derivative with respect to just theta 1, right? It's not the same thing. So we'll take all these constants out front. These 2's will cancel each other out. So we'll have m1 times L1 times L2, L1 times L2, L1, L2, theta 1 dot, theta 1 dot, theta 2 dot, theta 2 dot, and then the cosine of theta 1 minus theta 2. So when we take the derivative of cosine, we will get negative sine of theta 1 minus theta 2. Right? And then this isn't just theta 1, so if we do the chain rule, this is a constant, so we just get 1 if we take the derivative of this argument here. But it's always good to check, make sure that you're not missing a chain rule. So here's our first term, right? dl d theta 1. This is our first term right here. And now for these ones, I'm going to sort of take a shortcut and combine these into one term, because they're both just cosine theta 1 by itself. So we can sort of combine these if we ignore the other ones. So I'm going to say minus, because when we take the derivative of these, we'll get a minus sign. Right, so let's check the first term. There's a negative sign here, a negative sign here. So that's two negative signs that cancel each other out. And then when we take the derivative of this cosine, we'll get another negative sign out, because it'll be negative sine theta 1. And the word sine is popping up with multiple meanings here. But when we take the derivative of this, it'll be negative. There's two more negatives, so altogether it's negative. Two of the negative signs cancel, and then there's one more negative. Right, and the same thing for this one. Here's a negative, here's a negative. This one will add another negative, so it'll all together be negative. So the whole thing will be negative, and that's why I'm putting this here. And then there will be these two terms in here. So we're factoring out a cosine theta. Cosine theta times L1. m1g plus, or we could factor out a g as well. Why don't we just do that? Plus m2, rewrite my 1 here, right? And then this is a sine theta 1. Right, so we already took care of all of these negatives, right? There's a negative out here. M1, M2, and I forgot I'm going to give myself some room here. Right, so there's, I'm not sure what I just said, but I forgot the G and the L1 that appear in both of these terms, right? I'm doing these together. I'm sort of trying to save time. I might be using up more time by explaining it and not writing it. But anyway, G L1 sine theta 1. So you can see that these terms are in common, and so there's just an M1 or an M2 difference here. So this is L1, so this minus this term here, and then that should all equal 0. So maybe I should draw a line here. So this is we're just plugging it into the Euler-Lagrange formula. Right, and so dl d theta 1 dot, right? I'll write the d dt out, and we'll do that second. D dt, and now we're going to look at this derivative when it's valid in here, and then we'll write it out, and then we'll do the time derivative. So let's see. So theta 1 dot does appear here, so we'll take the derivative with respect to this. So it's theta 1 dot squared. When we take the derivative of that, we'll get a 2 up front, and then we will just have a theta 1 dot to the first power. So I'll rewrite this term. Actually, I'll just copy and paste again. Copy and paste. Right? So the 2 came up front and canceled this 2. That's why I didn't copy that 2. And now I'll erase this. So the 2 came down and canceled out the 2 in the denominator for that term. So that wasn't too bad. And now we can look at this term here. So we see that this one contains the theta 1 dot. So I'll just rewrite this one. This one is, and this one's going to look the same, right? It's going to have a 2 come down and cancel this 2, and then we'll have a first power, but it'll just be M1 times that stuff. So actually I will, I'm utilizing the copy paste quite a bit here. Copy paste. I'm going to add this. And then this is M2. Alright, now let's keep looking. So we can see that these terms only depend on the values of theta, not on the time derivatives of theta. So there are no theta dots here, so we can ignore these. And the last thing we need to do is right here. And since this just has a theta 1 dot to the first power, the derivative of this term here is just it rewritten without the theta 1 dot there. And in my usual laziness, I will, well, no, I'll rewrite this one. So this 2 cancels this 2, so I don't have to write out the 2's. Right, this 2 cancels this 2 if we distribute it in. So M2, so it's M2 L1 L2. So plus M2 L1 L2, right? And we're taking the derivative with respect to theta 1 dot. So this one goes away. And then we have theta 2 dot times the cosine of the difference. So theta 2 dot times the cosine of the difference of the angles. So theta 1 minus theta 2. And that all equals 0. Alright, now we have to take the time derivative of this, so we'll rewrite it. I'll copy and paste the top part since we're done with that. Copy and paste this. Copy and paste this. So and now let's take the derivatives here with respect to time. For these two terms, nothing that strange happens, right? These are just constant times a function of time, and we can just add another dot here. So I'll copy these ones. Right, copy these ones down here. And there's a minus sign out here. Minus. And then I'll add another dot to each of these, right? So theta 1 double dot. Take the time derivative of those terms, and then make sure the minus is distributed. And then for this term, theta 2 dot is a function of time, and so are theta 1 and theta 2. So it turns out we need to use the product rule. So minus, I'm going to copy and paste these because they're constants. So those come out front. And then we need to do the derivative of theta 2. So theta 2 double dot times cosine of the difference of the angles. So I'll chop this out again. Alright, so there's one part of our product rule, and then the other part of our product rule, give myself some more room, is theta 2 dot, so plus theta 2 dot times the derivative of this. All right, and what's the derivative of this? Well, it's the derivative of cosine is negative sine. So you can say sine, and this should be negative, sine of theta 1 minus theta 2. Right, and this is a negative sign. Negative plus the derivative of what's inside here, or times the derivative of what's inside here. So the derivative of this is theta 1 dot minus theta 2 dot. We're just rewriting it just with dots. Theta 1 dot minus theta 2 dot. Theta 2 dot. Right? And now we're done with that term. So I've stretched it beyond where we can see the whole thing. I'll just fix that with my handy copy and paste tool. Or cut that, and I'll paste it here. Alright, so all of this together equals 0. So now if we look closely here, we can see that this term here actually cancels with a term in here, right? We have, oh, now I've written an M1 as a red one, so let me check if that's actually supposed to be like that. So M1 times the sign. So it looks like it's supposed to be M2, so I wrote it in red, which was correct. M2. So this is M2. Right, M2. This is M2. Right, so these do cancel. So M2, L1, L2. M2, L1, L2. Then there's this term with theta 1 dot times theta 2 dot times the sine of the difference. Well, here's a term with theta 1 dot, theta 2 dot, and the sine of the difference. So this actually cancels with this. So I can write, so without writing it out again, we can see that if we separate, if we distribute this binomial, right, we'll have this term with the theta 1 and this term with the theta 2 dot squared. This actually cancels with this whole thing here. Right, they're the same thing. So here it's negative, this is negative, negative, right? So this is a positive here. So this term, if we multiply all this out, this will be a positive term with this. This is a negative term that looks the same. So they cancel. So one big chunk went away. So now let me rewrite this one more time in the simplest form we're going to see it. So what do we have here? m1 plus m2, right? m1 plus m2. m1 plus m2. m2. Put this in parentheses, right? There's a negative. Actually, I'll cancel all these negatives. Make all of these things positive because it's divided by 0 or equals 0, right? So we'll multiply the whole thing by -1, right? Plus, plus, plus. Here we have a GL1 sine theta 1. So a GL1 sine theta 1, right? And then we also have, actually, I've come this far, I might as well stay consistent with the colors, sine theta 1. And then here's an L squared theta double dot. They both have this term in common. So plus, so L1 squared, L1 squared theta double dot. Theta 1 double dot, right? So there's an m1 plus m2 multiplying both this L squared theta double dot and this GL sine theta. So whenever you're getting toward the end of a problem, it's always good to make sure that the things you're adding together have the same unit. So let's check this. This one is L squared, so that's meters squared, and this is angle, which is in radians, so there are no real units here, and then there's 2 time derivatives, so that's units of 1 over time squared. So this is length squared divided by time squared. And here we have g, which is, you could say it's in meters per second squared, or it's in length divided by time squared. And then when we multiply that by L, this is length, so we get length squared divided by time squared. So these are the same units, so that's promising. And sine, the sine of something, the sine of an angle, it's unitless, just like the angle itself is considered unitless. So this is a short, sweet version of all of these things together. And I should draw another line because of, actually I want to do it in white like I've been doing. All right, and then we can rewrite this having this canceled term here. I have m2 L1 L2, and then we have a theta double dot, theta 2 double dot. So we'll use this theta 2 double dot cosine theta 1 minus theta 2 minus theta 2 dot squared of the sine of the difference, right? And actually this is a plus because this was a minus sign here, and this is a minus sign, so minus minus turns into a plus. The sine of the difference of the angles. The sine of theta 1 minus theta 2. All right, and these 2 terms almost look like they could combine into something, but this is a little bit different, right? This is the second derivative with respect to theta, and this is the first derivative of theta 2 squared. So these both have units of 1 over time squared, and all of these terms have units of energy, right? This term all combined together, mass times length squared divided by time squared, mass times 2 lengths, length squared, divided by time squared. So these are all energy, all the same units. So that's at least one thing to check to make sure everything works out. So now we have this second order differential equation, right? It has derivatives, it has 2 derivatives with respect to time, and it actually has theta 1 and theta 2 in it. And if we did this for another, so if we apply the Euler-Lagrange equation for theta 2, and we went through more or less the same steps, we would get something like this, and then we'd have a pair of second order differential equations that we could solve to find the motion of this thing, this system, with certain initial conditions. So actually we're still quite a ways away from actually figuring out what this thing looks like, but we found the differential equations, and now we can sort of hand it to a mathematician if we want to think of it that way, and they'll be able to do it for us. Or ideally we could do it ourselves, but we certainly won't in this video. It's already long enough. And this is a crazy enough differential equation where you'd probably use a computer for it anyway. And if you go on Wikipedia, and you look at the page on the double pendulum, there's a nice little video or an animation of this thing kind of swinging around, and it looks kind of crazy. So I encourage you to go take a look at that, and then on your own try finding the differential equation that comes from applying the Euler-Lagrange formula to the other generalized coordinate, the theta 2 coordinate.